morning all, lecture 30, Introduction to Order Theory. This will be about first fit algorithm. So first fit is a simple and natural thing to study in any kind of online coloring game. In online chain partition game, it identifies chains colors with positive natural numbers. And whenever a new element is introduced, it uses the first legal chain. And although we already have seen that it's, in general, this first fit is bad, but it might be, and it is, a good subroutine in some more complex setups. So today we will see what happens when we apply first fit to interval orders, and then we will try to build on that, going to broader classes of posets. So first of all, let's underline that first fit does not depend on any kind of representation. So on one hand, if we have interval orders in mind, we can as well think that we are given intervals, because the first fit doesn't look at it. So, and it is convenient for us. We can also, we should keep in mind that it works in the other direction. So we are not talking actually about online chain partition game. We're just online coloring the incomparability graph. Yes, because first fit also doesn't look at the. It just uses the first possible chain, and you can judge if it's possible just looking at the incomparability graph. So, because this is so simple, we can actually forget about the whole game and study offline colorings here. So, given a graph G and it's coloring, and coloring of vertices into k colors, this coloring is a first fit coloring. If well, I didn't write it, but if it's proper, and we have this supporting property. So for every vertex, say it's color I. And for every color smaller than I, for every color j, there must be a reason why v is not colored with a smaller color. So there must be a vertex w, such that w is colored with the smaller color j, and vw are adjacent. And then there is a reason why v wasn't colored with I. And you see, and that's it, that's the first fit coloring. So we kind of forget what is, for example, the presentation order of the vertices, because it doesn't matter. At the end you can imagine that first all the vertices colored 1 were presented, and then color 2, color 3, and that's what first fit algorithm would do, would end up with this coloring C. Okay, so that's convenient, and this first fit coloring in the context of interval graphs is sometimes called the first fit wall. And the reason is that we can envision colors as kind of levels in the plane, and then intervals are like bricks now. Yeah, instead of an interval, I present a box of height 1, and then you see that every box on level I is supported by boxes on previous levels. So this is on level 3, yeah, and it is supported by a box on level 2, and it is supported by a box on level 1. Okay, so so let's first see that first fit actually makes some sense, playing on interval graphs, on intervals. So let's see that we're using a function of the optimum number. colors. So given interval orders of width at most W, or you can think of, just like I said, a family of intervals of click size at most W, first fit uses at most W squared colors. So in order to prove it, we will come up with the bound, which is a function of W, and this will be an upper bound on the number of colors used by first fit in this setup. So on collection of intervals of click size at most W. So we can set up this function, when W equals 1. So what I'm representing is just a disjoint set of intervals, of pairwise disjoint intervals, or if you look at the poset, it's just a chain. And then one color is enough, and first fit will keep using this one color. So this is a good upper bound. Yeah, this is actually the exact number, right? And then for W greater or equal to 2, let's try to see it in the context of the wall, of the first fit wall. So let's look at the largest number used by first fit, the highest level, yeah? And let's look at the brick on that level, yeah? So here is this interval, which is a brick now, yeah? And it's on some level K, yeah? And first fit was forced to use this color. So what we can see here is that on each preceding level, there must be a brick supporting this brick, yes, by the first fit property. And now some of these bricks can go through the left endpoint, yeah, on some levels. Some of them could go through the right endpoint. Yeah, maybe some of them go actually across, is possible. And also, supporting bricks could be just simply contained in our interval of a vertex V, yeah? So now, observation is that the number of bricks that support our brick V crossing this, pierced by the left endpoint, is bounded by the click size, because they all form a click. So it's at most W minus 1 of them here, red boxes, yes, not counting the white one. And here as well, at most W minus 1, yes. So now if we have this first fit wall, please imagine that we kind of filter it out. So we just get rid of all the levels, all the red levels, yeah? Yeah, we just filter them out, we remove them. And we look at what remains, yes? So these things supporting stuff in the middle are not red, yeah? I remove all the red levels. All the bricks that received color I, such that that this brick on level I is supported by something that goes from the left or right endpoint. So when we remove some layers and we look what remains, it's easy to see that this is still a first fit wall, just lower. So, and what is the property here? Well, okay, maybe I convince you that this brick is still supported, yes? Although it's easy, right? I mean, it is supported, and all the bricks supporting it are actually contained in it. So, okay, so what I want to do is we filter out red levels, or you could think of them as colors. Yeah. So remove them from the considered graph. And the second thing is that restrict only to intervals contained in D. Yeah, only those contained in the white one, yes?
Those red are just clicks on the ends?
Well, there could be some, guys still here or outside, yes?
Oh yeah.
So remove all of them.
They're colors, yeah?
Yes. So these are all the intervals that receive color I. Yeah. And so yes, so we narrow down only to these that are really not on the red levels and are completely contained in the white. Yeah. So what do we know about them? Well, if we just look at the yellow, the click number goes down, right? Because any click in the yellow we can extend with the white interval. So this means that the height of this yellow first fit wall is bounded by f of w minus 1. And that gives us the bound, yes? Because now we see that fw is at most 1 for the white level, 2 times w minus 1 for the red levels on one side and on the other side. Some of them could coincide, but then it's only better for us. And then the remaining thing is of height at most, the yellow thing is of height at most f of w minus 1. Yes? So we see that this is 2w minus 1 plus f of w minus 1. So f of w is just the sum of first w roughly odd numbers. This is exactly. This can be proven that we can prove by easy induction that SW equals W squared fulfills it, which closes the proof. Okay, so that's an easy argument. It already shows that first it makes sense in this setup. Now we're going to see the best known bound for first fit working on a collection of intervals. So first it uses at most 8 W chains on interval orders of width W. And we're going to do that not only because this is best known. There's a number of incremental results on this topic. But we do it because the proof is just out of this world. It's after all not so difficult, but I never seen something even similar to that. So the authors called the procedure that happens here a column construction method. You will see in a moment why. So let's have a look at the proof. We're going to study a collection of intervals which forms a first fit wall of Well, we're going to consider any first fit wall, and we're going to show that its height is bounded, yes? So we take a first fit wall, its height, so the number of levels or the number of colors is m, and our goal is to show that m is bounded by an announced function of w. Now, what we're going to do first is we're going to pierce our intervals with vertical lines. And we want to use the least possible number of lines. So this is equivalent to say that we take the canonical antigen, the composition of a poset, yes? So we have L lines from 1 to R, yeah? And they pierce all the intervals, and it's least possible, yes? They hit all the intervals. And they are ordered from left to right, yeah? This is the first line, this is the last line. And now in this setup we are going to we're going to look at columns that are growing along the red lines. So the thing will be that the columns will grow. So each so you should think that each line actually is not a line now, but it's like a very thin column, yes? So, for example, this one, yes? It's a column, yeah? We can stretch the drawing so we can have this one, yeah? And now, all the columns will be alive on level 1, yeah? C1 contains all the indices from 1 to R. And now, these columns will grow level by level. Some of them will drop out, and eventually we'll get an empty set where all the columns will die. Yes. So yeah, the columns are growing. Yeah. Some of them could get short. Some of them will be higher. Eventually, all of them will be gone. What will be the rules? Well, maybe before the rules, the important thing is that if the column is alive on level I, it has a label on level I. And the label is, so the column S, at level I, has a label. The label could be a letter R, $sign, or letter F. So, yeah, so in these cells, yeah, like here, so this here, you will see in a moment, we'll have a label R. And now, as long as column is alive, in each cell, it gets a label. So okay, so let's have a look at the rules. So as I mentioned, when we start, all the columns are alive along each line, and the labels, yeah, on the first of the first level cells is either R or $. So actually, so R is we put R every time there is actually an interval or a brick on level 1 that is hit by the column. Yeah. Then we put R. That's why I put R here, because there is an interval. Yeah. And if there is no interval on level 1, we put a $sign. Yes. So for example, this column here, yeah, this column here would get the $sign, yeah? Maybe let's change that. This is a $sign, yeah? Okay, so that's it for the first level. Now we will give rules how the column grows. But first, let me just note that there are no 3 consecutive $signs. It will be important at some moment to have this property at the very base of the construction. So this comes from the minimality of our lines. Yeah, that this comes from the minimality. Why? Because well, envision that. So here is a $sign, and envision that there is a column here with a $sign. and the column here with the dollar sign, yeah? So, yeah, so this is dollar, and this is dollar. Well, recall that dollar just means that there is no interval on level 1 hitting this line, that is hit by this line. But the choice of the lines is minimal, which can be translated to the thing that each line has a witnessing interval, such that it pierces this interval and no one else pierces this interval, because otherwise the line could be dropped. So this middle line here, with the middle dollar, has a witnessing brick, yeah? And the brick is sandwiched between the two other dollar sign lines. But this brick has no way to be supported by a brick on level 1. Yeah? Because there is no brick of level 1 here, here, nor here. Yeah? And bricks of level 1 also have to be pierced by the red line. So it could be here, but it cannot extend here. And from this side it cannot extend here. So this one is not supported by the first level brick, so it's not a first hit wall. Yeah? So this way we proved there are no free consecutive dollars. Okay, so let's move on and let's see how the columns grow. So given that we have already a set of columns that are alive on level I minus 1, and given that the set is still non-empty, we can consider what remains alive on level I. So for each column that survived so far, yeah, so you could think of here a drawing like this that we are talking about. Here it was I minus 1, and now it's level I, yeah? And there are some columns, perhaps, that are alive, yeah? Some of them are gone, maybe, yeah? But some of them are alive. And now, so this column is the S column, yeah? It corresponds to line LS, yeah? And now if LS is hit by an interval on level I, yeah? So if we have a brick here simply, right? Then the column survives on level I, yeah? And it receives label R. Okay? R for that is for real, that there is a brick behind it. Okay, and that's it, yeah? So maybe this brick extends here, so that would mean that this column is also surviving, yeah? Sign R. And this will be all the columns that survive and get labeled R on level I. Now, some of them can survive with a different label. So think of columns that are alive on I minus 1 but didn't get to I yet. So if one of their neighbors, yeah, so you think now about the column S, and maybe this is the column S now, yeah? Maybe this one, yeah? And then, yeah. If one of the neighbors of S on level I minus 1, okay, and what is a neighbor? Well, there is this is quite intuitive, yeah, so there is a natural ordering of columns, and when we look at only the columns that survive, there is a natural ordering of them from left to right. So each column, except those extreme on the left and on the right, has a column to the left of it that survived, and a column right of it. So the two neighbors of this column is this one and this one. Yeah? Neighbors on level I minus 1. Notice that it could have some different neighbor before, but that neighbor dropped out. And then there is a new neighbor, right? So if one of the neighbors of our column already made it to level I with label R, so made it with the first rule, then our column also makes it, and it receives a dollar sign. Dollar sign means could carry the intuition that okay, it survived, but someone is paying for it. Yeah, and it's the neighbor that survived for real. Yeah, is paying for it. So the column could get dollar sign because of the right neighbor or because of the left neighbor. Yeah, one of them has to survive with R. Okay, and that's the second rule. Now some columns still survive and get the label F, which you could translate maybe to fake. Yeah? Interpret as fake one. So what is the third rule? So for each column that got to I-1 and didn't get yet to I, if and for each neighbor, so L, neighbor of S, on level I-1. So let H be the first level such that L and S are neighbors. Yeah, okay, so maybe immediately we draw it. Yeah, so we're thinking about column S. Yeah, it got to I-1, and maybe we have a neighbor here. Yeah, that's our L, and then maybe that neighbor is a neighbor from this level here. Yeah, this is level H. Yeah, and this level here that they are alive is level I-1. Yes. So this is the H. That's the first level that S and L are neighbors. So now, if the number of R's in column S in cells from H to I-1 is greater than I minus H over 4, then we had S survives and it gets labeled F. So
RS.
Yes. So R of S. So given a column, yeah, that survived, and we have some levels here. So say this is level A, and this is level B. Yes. So and this is column S. Yeah. So R S of AB is the number of R's in this segment here. Number of R's in this segment. So here we are thinking if S survived, and S could survive if not for these two reasons. S could survive because it has a neighbor, such that when you look at the piece of S that is neighboring with the neighbor, here I'm looking at the right neighbor. So what is the size of it, yes? If you count the number of cells here, you see that this is exactly I minus H. I minus H cells are here. And if more than a quarter of these cells are R's, then we say, okay, S is rigid enough, it won't collapse, let it grow. And you put F on top of it, and you get into level I. And that's the third rule. And we let the columns grow. So you immediately see from this context that if a column is not making it to CI, it is not reappearing anywhere in the future. So indeed we are going into subsets. And then you can also see that it eventually gets to the empty set. This is simply because above level M, yeah, and M was the height of our wall, there is nothing that gets an R symbol, nothing. So there will be no dollars, no R's, because dollars are because some neighbor is getting R, yeah? And there will be only F symbols, but F can be received if the stuff is rigid enough. But if you grow for some time, the number of F's will decide, and everything will pass out. Okay, so that's quite a fancy way to build to try to pierce some intervals. The first thing we want to see actually here is that every interval gets pierced by a column that is alive. Yeah, because the lines are piercing the intervals, but maybe some interval up there is not pierced by anything that actually grows. It is. So this is the first thing we do. So claim 1. Every interval is hit by some column. So we're going to prove, and let me mention it before we are actually proving it, you can keep it in mind, that to have this property we don't need actually the third rule. We don't need F's at all. It would be enough to just work with R's and dollars, and the column would grow to hit all the bricks. Yeah? So let's see, we're going to prove something stronger, kind of double induction. So for every j that goes over the levels of our wall, and every I that is between 1 and j, every interval in our family I is on level j is hit by a column, or maybe let's write it formally, is hit by some line ls with corresponding column alive on level I. Okay, so once again, let's depict what are we actually doing here. So first of all, we have a level j, and we'll consider interval on level j. Yeah. So here is our brick. Yeah. That's our interval. Say, let's call it v. Yeah. And it's on level j. Now we're going to look at the level I, yeah, which is less or equal j. Yeah, so it could coincide, but let's draw it that it doesn't. So let's think about the level here, okay? And now we want to show that there is a column that is still alive on level I, such that the corresponding line hits our interval v. Yeah? So we want to show that there is a column, there's at least one column that gets alive here. Yeah? We know that there is a line, yes? We know that there is a line, but maybe the corresponding column drops out. I mean, actually not, there is something that gets alive here. So you see, this will be induction, and when it's carried over to j, there is a column that hits interval v. Okay, so we're going to prove it, and when j is equal 1, yeah, then I can be only equal 1 as well. Then this comes from the fact that actually the lines were hitting all the intervals, so in particular all the intervals on level 1, yes? So there is a line that hits it, yeah? And this line, by construction, is alive here, yeah? It gets the R sign, which is irrelevant. It's just alive. So every guy is hit. So j equals 1 works, and also for any j greater equal, say already 2, and I equals 1, it also works. This is more interesting a bit. This comes from the $3 property I mentioned, because so you look at now you look at some interval which is high there on level j, yeah, and you just want to see that some column. Oh no, that's actually trivial again. Sorry. That some column survives on level 1, but this guy is supported by a brick on level 1. Oh, okay, this guy is supported by a brick on level 1. So, okay, so this brick could be, for example, here, and then this column would get survived here. That's easy. But we have some interesting here case to see that the brick could support it this way. You see, yeah. And then the line, the column would be here, right? And this would get stay alive, yes? So this is not enough. But we know that there is a line that hits our interval v, yes? So if this line goes through the intersection of this brick, then obviously the column survives on level 1. So what happens if it doesn't? Yeah? You could have even a number of lines here. What happens if they don't survive? Okay, maybe I got it wrong, because I actually said that everything survives on level 1. Just if it's not with R, then with a dollar sign. Well, okay, then I actually, if I put it this way, and I did put it this way, then this line simply gets a dollar sign, and it's ready. Okay. Apologies, I got it maybe I took a detour to get here with an easy thing. So we got a base. And now we want to see what happens if j greater equal to and I greater equal to. Okay? So let's look at this picture. This will be our general picture here. So, what do we know? We know calls here, 2 inductive calls. So first, this brick is supported by something on level I, yeah? By some brick on level I. And, okay, so this brick on level I, yeah, it could look like this. Could be contained in it. This will be an easier case, yeah? Because then, by inductive call, this brick on level I is supported by some column that gets to I. Yeah? So it must be like this. Excuse me. To level... Yeah, as simply as like that, yeah? It gets supported by level I, and this is the column that survives to level I. That is piercing J, yes? So this is easy, but obviously, interesting case is if we have this brick supporting our brick gets away, and then this is the column, yeah? This could be like this. So now we need to keep working, yes? And now we use the second inductive call, and we know that there is some column that actually supports our interval V that gets at least to I minus 1. Yes? And now, if this column that gets to at least to I minus 1 is also below this brick, then it gets survive here, and this will be it. So let's immediately get to the case where it's somewhere here. So there could be a number of columns like that. Yeah? They got survived to I minus 1. And we want one of them to get to I. And now will come the rule of the dollar. Yeah, because we have this column here, and maybe there are more. But we take the rightmost column over those, and here is the R sign. And we take the leftmost column here, and by the dollar rule, this column will get the dollar sign from this column and will survive to level I.
We said that if one of the neighbors has label R, but on level I minus 1.
So if one of the neighbors on level I minus 1. So that's actually perhaps a good point. So we look at this column, which is the leftmost of ours, yeah, here. And so if there is a column like this, then it will immediately get R and it's below V. So this is good. So the first column going from this end, which is interesting. The interesting case would be that there are no columns like that, which immediately means that on level I minus 1, so this is L, this is S, they are neighbors. Yeah, they are neighbors on level. There is nothing in between. So that's why the dollar sign here comes from the R sign here, R symbol here. Okay, so this closes the induction step, and we actually have the property. So you see, we didn't use even the third rule. Yeah. Okay. So now the idea is to show that one of the columns that goes up to the top, one of the largest columns has a substantial fraction of R's. So R symbol comes only if there is an interval there. So if there is there's a fraction, then the fraction of the height of the first net wall will be witnessed by a click of this size, and that would be it. And here it seems that it's important that we have the third rule, because it's easy to set up an example where the first fit wall is high, but the highest column actually have only dollar signs except the last R or something like that. and then, so this wouldn't work this way. Okay, so we're done with the proof of the first claim. Let's come back to the flow of the main argument. So let's define m prime. So m is the height of our wall, but columns, as we discussed, could grow even above that. So m prime is the height of the maximum height of the column. Yeah, and now we fix, so in particular we have that, this is by claim of 1, yeah? That our columns grow at least as high as the first bit wall is. And we want to fix a column, one of the highest columns, so we take S, which is in last non-empty level. And now the goal is, again, to show that the number of r's in that column, all over, so from 1 to m prime, yeah, is at least the height of it, so m prime over 8. Yeah? And then the number of r's by the construction are witnessed by the click. So it lower bounds the width of corresponding interval order, and this from this side. So this is okay. So this is our goal. Yeah, and from our goal we immediately get that if we get this, then m prime over 8 is at least m over 8, and on the other hand this is w, so we would be done. Yeah. Okay. So we so this is one of our highest columns. Yeah. And we would just like to say that here is at least m prime over 8 r's, r symbols. Yeah? Height is m prime. Okay, so what do we do with it? So we consider the neighbors, all the neighbors of S over the history. So there was perhaps a first column that grew for some time, and then the second, and the third, and maybe that was it, yeah? So that's the L1, L2, L3, yes? So in general, what are we going to do now is we want to bound the number, we want to lower bound the number of r's. So we start with upper bounding the number of dollars that we see here. And dollars come from neighbors, and I am looking at the left neighbors at the moment. So let LK minus 1, L1, which is all less than S, be all left neighbors And now we want to also record the heights. So we will have hk, which is greater than hk minus 1, which is greater than h1, which is greater than h0 that we set to be 0. And so the idea is, let me see that, that the level here is h1. So this level here is h2. And this level here is h3. Yeah. So in general, what we're having here is that for every I from 1 to k, so for all the neighbors, Li and S are neighbors on levels hi plus 1, no, on hi minus 1 plus 1 up to hi. Yeah, so for example, L2 is a neighbor of S from h1 plus 1 up to h2. Yeah, and then we have the second property, and the second property will come from the fact that Li dies at height hi. And this will tell us something. It will tell us that it didn't qualify for the F symbol rule. So we have that for every I from 1 to k, the number of R's in Li that is between hi minus 1 plus 1 and hi is less or equal, right? Because in the rule we had the greater equal. Yeah, there is a greater equal sign here, so this should be less or equal than hi minus 1 over 4. Okay, let's try to explain that. So have a look. So L2, column L2 dies at the level of h2. In particular, it didn't qualify for the F symbol. So the F symbol, for example, would be received if, when it looks to the right, it sees its right neighbor, so it's S, and it takes all the segment where it's the neighbor of its right neighbor. So that would be this segment here, right? If there are more than a quarter R's here, then it would qualify. So what is the size of this box, yes? Well, it's h2 minus h1, right? And then it didn't qualify. So the number of R's in L2 column in this box, in this segment, is at most quarter of the whole segment. Okay. So, so now you see we have bounds on the number of R's in the left neighbors, and it's R's that generate dollars in our target column, right? So we should be good now. The number of dollars in column S due to left neighbors it's at most the number of r's that we see on the left neighbors, yes? So it's at most sum over the neighbors, so from 1 to k. Yeah, the number of r's in respective neighbors on the segments that they are actually neighboring with S. And each term in the sum was actually bounded here. So we get that this is less or equal than the sum, yeah, of hi minus hi minus 1 over 4. Yeah, and it goes from 1 to k. So you see that it's a telescope. And so it's only the last one that survives. This is hk. And the 0 one, but 0 is 0. So this is actually equal to 1/4 of hk. Yeah? But the height of the neighbor is at most the height of the tallest column. So it's at most n prime. So we finally get what we wanted here, which is n prime over 4. The column is of size n prime, and there are at most n prime over $4 contributed by the left neighbors. Symmetrically, the number of dollars in S contributed due to right neighbors is at most n prime over 4. So finally, the number of dollars in our column all the way through is bounded by n prime over 4 plus n prime over 4, which is n prime over 2. Almost half of the column are dollars. Okay. So now we need to relate to the number of f's. Yes? And so here comes the second claim. That for every I that goes over the levels of the columns, and for every t, which is index of our column, such that t is alive on level I, we have that the number of r's in t up to I is at least a quarter of the number of r's plus number of f. So now, this is a rather weird way to state that free RT1I is greater or equal than FT1I. but this will be easier to get by direct induction. So we stick to it for a moment. Yeah, so okay, maybe I envision the statement again. So what do we have here is easy, right? So we just look at the single column, yeah, and we look at it up to some level I, yes, and now we just claim that the number of r's here, that the number of f's here are at most 3 times the number of r's here, yeah. This is what we claim. This is our column T, yeah. Okay, so we do it by induction, and this should be not so difficult. So induction on I equals 1. I equals 1 should be doable. So, yeah, R11 is either 1 or 0. Yeah, it's either R symbol or a dollar symbol. Yeah, so and what is the number of F symbols? It's 0. So this one holds. And now when we go to I greater or equal to, first thing to notice is that if label of our column is not F, then this is just by induction. Yeah, because look what we have. We just received the label F here, and by induction, no, we just received something different than F here. Yeah, so for example, dollar or an R symbol, yeah? But by induction we know that up to here, this holds, yeah? And the only way to break it with one more symbol would be to actually put the F symbol, yeah? But we did not, so it holds. So the only interesting case is that when label on this ith level is actually F, yeah? So what happens then? So let's assume that the column gets F here. So it qualifies for F. What does it mean? It qualifies for F because there was a neighbor up to I minus 1 actually, yeah, a neighbor. Yeah, such that when you look at the block, yeah, of time when these two are neighbors, yeah, and you look at our guy here, then we get that that the number of r's here. So there is a level j, yeah. Let j be the first level that they are neighbors, yeah. Then the number of cells in this box again is I minus j, yeah. And the column qualified for F only if at least if more than a quarter of the green segment here is with r's, yeah? So we get a good chunk of r's here, and this will allow us to go through the induction. So, how does it look? So then we know that there exists this j that I have drawn, yeah? Such that RT of from j to I minus 1, yeah, is greater than I minus j over 4, yes? And now this is obviously an integer, so I can replace it with the greater equal sign, and I can put here +1. At the top of the structure, yes? So now let's just go for it. So the number of r's in total in our column, yeah? Obviously we can split it to the number of r's here in the bottom and the number of r's in the green box. Well, we want to count it together with this actually, yeah? But we know that there is no r here, yeah? So the number of r's there is the number rt up to j minus 1 plus the number of r's in the green box from j to I minus 1. Now, by induction, this white portion here, we can get by induction that this is at least 1/4 of the RT, a number of R's in the bottom, plus the number of F's in the bottom. Yeah? And now here, we just use the fact that there are lots of R's here in this box, yeah? So we just put 1/4 of the size of this, of +1 that we noticed. Okay, so now when we mix it up, so notice that I minus j plus 1, yeah, so this number is actually the size of the green box together with this extra slot, yeah, I minus j plus 1. So this is just the size, so instead of the size, we can put the number of r's that you see here, what is it, from j to I, and the number of f's. You can also put the number of dollars, but this is irrelevant. Yeah? So we have 1/4, yeah, number of r's here, number of r's here, number of f's here, number of f's here. So this clicks to this is actually equal now, right? Well, okay, I made this step on the fly, then this is just equal to what we wanted, from 1 to I plus f's from 1 to I. Okay. As desired. So this is claim 2. And claim 2, as you see, relate number of r's to the number of f's. And this will be just enough to complete the proof. So yeah, that was our goal. Let's keep it. Okay, so recall that we are talking about the longest column. And in this column, we have r's, right? We have dollars, right? And we have F symbols, right? And in total, there are n prime of them, right? But now, if we just look at the r's and the f's, yeah, then this is n prime minus the number of dollars, yeah. But the number of dollars is upper bounded by half of the size, which means that this is lower bounded by n prime over 2. But now the number of f's is upper bounded by 3 times number of r's, so this is at most 4 times number of r's. And this this tells us that the number of r's in the longest column is at least m prime over 8. And this completes our goal, and as such completes the proof of the statement that first fit does quite well on interval orders. This is yet an open problem. What is exactly the multiplicative factor in front of it? So we know that it's 8w. It's the upper bound. The best known lower bound is 5 minus epsilon w. So for any epsilon greater than 0, you can get this construction, and that's the space. Some people believe that it should be 5, but since 2010, when this magical proof appeared, there was no progress on the topic. Okay, now we're going to see that first fit actually works on a much broader class of graphs. But we call that interval orders are exactly those posets that are 2 + 2 free. And in general, k+k-free structures are 2 chains, each of size k, such that there is no extra comparability between them. And first fit actually works well on k+k-free orders for any fixed k. So this is way above any kind of interval representation, and this class of posets k+k-free orders is something that shows up every now and then as a class that you can get this property working on your favorite class of posets, which is like defined in some geometric means, for example. You can get to this property, and then it might be useful to know that you can do something with those. So this is what we are going to do. We're going to see that that first fit works well for arbitrary k. So it uses at most this number of chains. So this is the width of a k+k-free order, w, and the number of chains is 8 times 2k minus 3. Now, for k equals 2, the statement just holds, because it happens even that 2k minus 3 then is 1, so we use, as we announced, as we have seen, 8 w chains. But in a general setup, we need to prove something, and actually the proof is quite instructive. So although we work with a much broader class of posets, we will see somehow their interval orders, and this is the interesting part. So that's the claim. One of the central claim, I think. There will be one more to complete the proof. So what does it say? So for k greater or equal to, every k+k-free poset that you can take, p, of width w, actually extends some interval order q where the width doesn't explode too much. It's bounded in k and w. So now the notion of a poset extends another poset could be not true for you. Here is a definition anyway. P extends q if they are on the same ground set, and whenever we have a relation in q, we have a relation in p. Yeah, so linear extensions extend poset. But now we consider some not necessarily complete extensions. And okay, so in particular we will get from this that when we have our poset p that extends q, then the incomparability graph of p is a subgraph of the incomparability graph of q. We're going to relate to that when we complete the proof of this claim. So once more, when we set up the proof, we look at k equals 2, and we notice that this is again trivial, because P itself is an interval order for k equals 2. So it extends itself if you really want to. And the width is W, as you would like to.
It should be inside the brackets, I guess.
Oh. Wow, okay. Must be so, right? But then, oh yeah, okay. Apologies. Now it's true. So we just look at k greater or equal 3. So you take your poset. It's k plus k-free. Now with W, so you take the Dvorkian partition, C1 to CW. And now we want to study this poset a bit. Yeah. And to somehow exploit this k plus k-freeness. So we want to look at the block of elements in the poset. So a subset X, yeah, is a block. If first of all it intersects each chain on a segment of size at most this should be equal sign. On a segment of size 2k minus 3. Yeah, basically. With exception to chains that are smaller than that, then you just take all the chain. Yes, so you want the block to extend just a bounded segment of each chain, and then as it's natural, you want this intersection to be a set of consecutive elements on each chain. Yeah, so now this is what we think of, yeah? In each chain we take a segment of the size 2k minus 3. Okay? That's a block. That's a block. And now given a block, we can look at the elements that are above this block. So those are those elements that are outside it, and yet they are above at least one element in the block. So you just, when you see the chains and they are cut here, you take all the elements that are there on the in the parts cut above. Yeah. And now an element is good in the block X. If it belongs to the block, you should rather think that it's low in the block. If it belongs to the block and it is below all the up set of the block, so all the elements that are above here. Yeah, in principle it wouldn't have to be below this one, but it's good. So by definition it is below everybody here, all the yellow. Yes, and now we're about to prove this property here, which will work on the k plus k freeness. Okay, so given a block X, and given that the upset is non-empty, there is something up there. Okay, there is some yellow element. Then there exists an index, so a chain, such that on this chain, there is something up there, yeah? The upset contains something of that chain. And the minimal element of the block and that chain is good. So you want this one to be good, and you want to have some yellow up there on the string. So this then, we simply say something like that exists. And so let's prove it, right? So first of all, we have a situation that there is something up there, right? But maybe not each chain is extended up there. So we should just focus our attention on those chains. Okay, so I don't distinguish it yet, right? Maybe some of the chains are extended, but some are not, yeah? So I just want to restrict my attention to those that have something up there. So let's renumerate the chains and let's have chains from C1 to CW prime, yes? After enumeration, so this is going to be, we are going to prove this now, the star property. Chains hitting, covering actually up of X, right? Now these chains are roughly of size, in the block are roughly of size 2k. So we want to distinguish their two chains of size exactly k. So here is one, and then so the bottom points here, they will be called, so this would be A1, yeah? In general, it is AI, yeah? Now, this is a chain of length k, I call it L1, in general Li, of bottom k elements, yeah? And then, so I have here still k minus 3 elements. I take 2 elements overlap with this chain, and I take this element. This will be k again. So I have something like that, and this is again a chain of length k. Let's call it UI, yeah, if it's the ith one. Okay? So you should know that since k is greater or equal to 3 actually, right, then, and this box is of size 2k minus 3, this is always at least k, yeah, because of this. So the blue guy always sits here, yeah. There is nothing weird. So okay, so we have like a lower chain and an upper chain for each eye on our chains that are extended above, because we are using this one element that is above. So we assume that it is there, yeah. So for each chain here, so for I from 1 to W prime, we produce Li and we produce up I, yes? And now I gave some names I want to, I guess, gave something more. So that guy is AI. Here we have 2 guys, and we want to call them BI and CI, and the top guy here is DI. Yeah, I remind you that the top guy is already outside the block. So the block is something like this. So this guy is the only guy outside. Okay, so now we want to find a good element. So we want one of the A's to be good. And in order to do that, let's consider an auxiliary digraph. So the digraph will be on indices from 1 to W prime, and we will send an edge from I to J if and only if AI is not less than DJ. Okay? And so the quick observation here is that the digraph is acyclic. So why is it so? Well, consider the opposite. Suppose that there is a cycle. Suppose the contrary, we have a cycle. So I1, arrows I2, arrows arrows I what? Oh, I'm missing letters. IN, yeah, maybe, and IN arrows I1, yeah. So okay. So what we want to prove now is that I want to start with B2 is less than C1 in our poset P, yeah? Okay, so let's see what's going on here. So we have A1, yeah. We have this chain. Here it ends up with B1 and C1. We have A2. We have this chain. It ends up with B2 and C2. We also have this chain here. Yeah. Ends up with D2. Now, well, okay, one is I1, 2 is I2, sorry, I dropped the I in the index here. And then, so what we have is that 1 arrows 2, right? So this means that A1 is not below D2. Yeah, so we don't have this comparability. But this blue and this yellow are two k-chains. And the poset is k+k-free. So if there is no comparability like this, there must be a comparability like this. So we immediately get actually what we wanted. Well, do we? Yes, because the chain starts with B2, okay. So we immediately get that from the k+k-freeness, we get that B2 is less than C1. Okay, so now I want to make a step, and I want to actually show that BI is less than C1. Yeah, for each I from 2 to n. Yeah, so I showed it for I equals 2. So let's continue. Let's just make a step and do for I equals 3, right? So in I equals 3 case, we have this third chain here, and this is B3 here, right? And this is D3. What I want to look at is this yellow chain, yes, this one, K chain, and I want to look at this chain. Let's make it red. Okay? So please recall now that 2 arrows 3. Yeah, which means that A2, which sits here, A2 is not less than D3 in the poset. So we don't have this comparability. But the red chain and the yellow chain are 2 K chains. So we must have the other comparability. What is the other? B3 less than C1. Yes? Okay. Yes? I took this chain and this chain. Okay, so this way we can move forward, right? And at the very end we have that. Bn is less than C1. But C1 obviously is less than D1, right? And Bn is greater than An. So we have that An is less than D1, but we have an arrow A1, D1. So it shouldn't be the case. So this is a contradiction with the fact that I assumed that we have a cycle in our diagram. So we don't have a cycle. We don't have a cycle. And then if there is no cycle, then what we should do is we should take the sink. We should take the sink. So take I in one double prime that is a sink in the diagram. Yeah, so there is no edge leaving I. There is no edge leaving I. What does it mean? So we have our CI. Let's say this is CI. Yeah. And then no edge leaving, so AI edge, an edge would be if AI is not below corresponding DJ. If there is no edge, so this means that AI is below all of them. So so it qualifies as a good element because it's below all the upset, and also there is an element here at the top that we also wanted to have in the property because we just looked at those chains that were that had extension above. So this completes the proof of the star. Okay. Now we need to recall what are we doing. So we are still proving claim 1. Claim 1 said that that P extends an interval order, and we haven't seen yet any interval order. But what are we going to do is we're going to define sequence of blocks. So P1 up to something like PQ, yeah, is a sequence of blocks. So B1 is just the union of bottom of minimum of the 2k minus 3 and size of Ci, smallest elements in Ci, and we do it for each chain I from 1 to W. Yeah, so what are we doing here? We are back to our chain partition, right? And we just chunk off the block of very bottom elements. Yeah? This is B1. 2k minus 3 of each chain. I assume that all chains are long enough. Now, how do we proceed with the next block? Well, as long as bi minus 1, so I is greater or equal to now. As bi minus 1 is non-empty, yeah, if bi minus 1, if the up set of bi minus 1 is, say, empty, then we stop. So we say that Q is actually the last one, is I minus 1, yes? But in the case that there is something yet up there, then we are shifting our block. Then what do? We find the good element, we find the star element. So we find the element which is or the chain if you prefer, we find this I such that we have a good element for the block P1 at the bottom, yeah, and there is a guy here, yeah, in the up. So and then, well, so let's give them names. So this would be U, this would be V, yeah. U is a good element. Of Vi minus 1, say, given by the claim, by the star property. And say this element is in this block intersected with C, J, yeah? So then V is the minimum of the upset of Bj minus 1 intersected with Cj. So V is this guy. And then we simply do Bj is equal to Bj minus 1 minus U plus V. Yeah? So we remove this guy, we add up this guy. Yeah, so B2, if you want to envision B2, you would have this, yeah, and that would be now B2. Okay? And this way, we are moving. And eventually we stop, and that's our sequence of blocks. So now we are really close to conclude. So, it should be clear that every element appears in an interval of the sequence of blocks. Yes. So that sequence we consider again B1 up to BQ, and now every element of the poset, yeah, appears in an interval of the sequence B1 to BQ. So now, given an element U in the poset P, yes, U belongs to P, we send it to an interval, yeah, IU, which is closed interval ij, such that U is in Bi up to Bj and no others. Okay? So now we have some intervals. And what do we have? Well, we need to see two properties. One, that this interval order, so this interval order is on the same ground set by definition, right? But we should see that its width didn't explode, and that actually P, our initial poset, extends this interval order. So let's start with the width. So consider an antichain. An antichain in Q. So Q is the interval order represented by these IUs, yeah, for U in P. Yeah. So now you consider an antichain in this interval order, And what do you see? Well, okay, let's give it a try. So you have intervals. Yeah, it's an anti-chain. Obviously, there is a point that hits all the intervals. So let's call it somehow. I don't know. Let's call it I. But this means that all the respective elements are in the block Bi. So if A is, I don't know, some A1 up to A size A, yeah, then each A, J belongs to Bi. Yeah. Well, okay, maybe, yeah, each AJ belongs to Bi. So in particular, A is a subset of Bi. Yeah, now I kind of coincide the notion of an element and its interval. I hope it's fine. But this simply means that the size of A is at most the size of Bi, and the size of the block is very clear, right? It's at most the width per W chains, and in each chain we have at most 2k minus 3 elements. So it's 2k minus 3 times W. So this bounds the width. So the width of Q, yeah, is indeed at most 2k minus 3 times W. So now the last thing to see is that P actually extends our interval order Q. And this should be clear, right? Because well, given that U is less than V in Q, right? This means that U has an interval, say, ij, and V has an interval I prime, j prime, right? And if we have this relation, then this is equivalent with saying that j is less than I prime, correct? But then, what do we know? We know that, first of all, V is not in Bj. It shows up later. So V is actually in the up of Bj, yes? And now U has J in its interval, so actually U is in Bj, yes? But look at that, U disappears at J. It's not in J minus plus 1. Yeah, U is not in Bj plus 1. So what can we say about U that disappears? It's good. It's good in the block that it disappears. And what can we say about good elements in the block? U is good in Bj. This means that U is below all the upset of Bj. So in particular, U is below V in our initial poset P, which means that P extends Q as desired. This completes the proof of claim 1. We are done with the claim. Are we done with the theorem? Well, we know that incomparability graph of P, our k+k-free poset, is a subgraph of the incomparability graph of some interval order Q. And we know that on interval graphs, yeah, in Q is an interval graph, we have a good bound, yeah? So is it true that the first deduces A times the width, where the width is here 2k minus 3 times W chains, and that's it? Is it true? Well, what are we dealing with? Again, P, k+k-free with W. We know that incomparability graph of P is a subgraph of an interval graph of this click number, or corresponding poset of this width. Is it enough to apply the 8W bound? Well, no, not at all, because this is tricky here. Subgraph. So think about the first fit for a moment. How does first fit behave on the complete bipartite graph? So color 1, and then if you present something on the other side, color 2, yeah? On this side, color 1, on the other side, color 2, right? So it uses all the time 1 here and all the time 2 here. 2 colors on a complete bipartite graph. Look at the subgraph of it. Complete bipartite graph without the matching. I already presented you that example last time, yeah? You start color 1. Here, this time it's color 1, because there is no edge. I present the other vertex. And then here you get color 2, and you copy the color 2 here, and 3, and 3, yeah? So this is K and N, just without the matching, without the perfect matching. It's a subgraph on the same ground set, vertex set. Yet first it explodes. So it's not true that if we have a bound on an interval graph, we have immediately a bound on a subgraph. Well, in the interval graph case, monotonicity is true. Maybe not so direct one, but this one. So for every graph G, that is a subgraph of an interval graph. And that interval graph has bound on the click number here, so W. Then for every such graph that is a subgraph, there exists an interval graph, H, with the same bound on the click. There exists one. It's not necessarily that supergraph itself, but that there exists one such that first fit, when you take the first fit number on the graph G, so the maximum color that first fit is forced to use on G, it lower bounds the first fit on H. And H is an interval graph. Clearly that's good enough for our purposes. So let's just go into the proof of claim 2. It's not hard. So just consider a first fit coloring of our initial graph G. And take the one that forces the first fit to use F and G colors, yeah? Then that's the color partition, yeah? The B1, BC, yeah, that's the C independent sets in G, yeah? Color classes. And now we have an interval graph behind it, behind G. There is a supergraph, G prime. It's the interval graph. That's on the same vertex set, and the click number in the statement was bounded on that one. So okay, we have interval graph, we have interval representation, so we have intervals. Now, when you look at the color class in G, yeah, and you look at the corresponding intervals, right? So, yeah, you can think of the red color, right? So there could be intervals that intersect and have the same color, right? Because it wasn't simply an edge in the G. And first fit applied the same color, because it could, say. So that's what I'm saying now. When I look at the color class, like the red color, VI, I want to partition it into connected components in G prime VI. When I look at the red subgraph, it's not an independent set anymore. Might be. So there are connected components. And just split them into those connected components. We have a number of them. Yeah? And now for each component, the red connected component, that would be 1, yeah? But maybe there is another one here, right? Here, like this. The second one. For each connected component, I want to take an interval representing it. And it's just the union of all intervals that contribute to that component. So the interval for this connected component would be just this big red interval, and that would be another one, yeah? So these are the connected components, Wij's, and these are the intervals representing them. And they are intervals, they are the union of intervals, but since it's connected, then the union is also connected. Okay, so, and family of intervals like that, we have red intervals, but we have intervals for each color, is our new family of intervals, and the interval graph represented by that is our target H. So H is an interval graph represented by ij. Yeah, and now I runs over the color classes, initial ones from 1 to C. And J runs over the components in the color class I, so from 1 to Ni, yeah? Okay, so that's clearly an interval graph because it's defined by intersection of intervals. And now, what do we want to see? Well, first of all, we want to see that the width is bounded. So, well, the click size, click number is bounded, yeah? So we will have that it's at most W. That's first property. And the second property is that first fit is forced to use loss of colors on this interval graph. So we will actually build a wall here, or a first fit coloring that is inherited from our initial first fit coloring. So we can just define it ahead. So the color of an interval Iij is what? It's just I. Okay, so we claim that this is a first fit coloring. And since every color is present, yeah, because every initial color contributes some connected components, and they are represented by intervals in the new graph. So the number of colors used here is the same as the initial number of colors, yes? So this will uses the C colors, and this will prove that FH is lower bounded by C, right? Because we will produce a first fit wall of height C. So that's the two items to show. This one, and that this is a first fit coloring, yes? Okay, so this is fairly easy, right? Because if you look at the click in H, yes? So click in H are just intervals here that pairwise intersect, yes? Correct? So there is a line that they all share. And now each of these intervals is of the form Ij, yes? I comes from a color, like red, and J from a connected component, yeah? This means that, this guy is the union of small guys. And there is a small guy that is here, right? And then there is a small guy that is here. I'm using a different color because actually it cannot be red. Because if it would be red, it would belong to this connected component here, right? So in particular, they are distinct. And that's what I need here, because I'm recognizing intervals in the original interval graph in G prime, yeah, that form a click. But there the click is bounded by W. So our click number also is bounded by W, as desired. So now we have here the coloring of the big intervals, yeah? And then it's inherited, yeah? So this guy is actually red, and this is actually yellow, and so on, yeah? And we want to show that it's first fit. So you have a red interval, yeah, and you can think of that this is color 100, and you want to see that it's supported with intervals of lower colors. Is it true? Well, that's very easily true, because this guy is a union again of some red guys in the G prime, yeah? So maybe it's just one of them, but maybe there is a small guy here. So maybe you just prefer to think about this guy here. So this guy got color 100 in G. So it couldn't get color 99. Why? Because it was adjacent with something. So G is not necessarily an interval graph, but it's a subgraph of interval graph. So it means when I draw these intervals here of G prime, yeah, I don't necessarily have an edge in G. But all the neighbors of G, all the neighbors of this vertex must be intervals that intersected, must be contained here, yeah? So this means that among them I must see some guy of color 99. And now this guy, little guy of color 99, contributes to the component of color 99 in G prime, yes? And this component, yeah, it could be a larger interval, but definitely this interval intersects the red interval. So that proves that our coloring is first fit. And that finally completes the proof of the theorem, which says that the first fit does well on k+k-free posets. I mentioned at the beginning that first fit can be used as a subroutine, and I want to conclude with this online stuff showing such case. So we're heading for this theorem here, that we can color online convex sets spanned between two lines coming online with a number of colors that is cubic in the optimum, which is the click number. So maybe it will become clear if we put it in the context. So we know that incomparability graphs of posets are represented by intersections of curves spanned between two lines. And special classes of posets have nice curves, like two-dimensional posets are represented just with segments. And three-dimensional posets you can do with these one-bend curves, where the bend is along one fixed line in the middle, say. And in the interval order graph case, the curve is actually a rectangle. Yeah, and obviously it gives you the right intersection pattern. So we are talking about a thing here which generalizes interval graphs, generalizes, well, orders and two-dimensional orders. That's orders that are represented by convex objects. Now, we don't insist that that's the same object. I mean, each element could have its own convex body. What we insist on is that it touches both lines, yeah, and it's convex. So and here are also what we know about online coloring of these graphs that are presented with representation. Yeah, actually, it is not easy. It is easy to see that even if you present posets with the representation of the curves, you don't help the algorithm at all. It's the same problem as you would present an abstract poset. So general bound is all we know. And in the interval case, we know that it's 3 omega minus 2. Yeah, first fit does 8 omega. Yeah, but there's an online strategy to do 3w minus 2. And in the two-dimensional case, actually, I didn't write it, but we know that it's exactly omega plus 1 choose 2, right? And in this case, we will build an algorithm that defends the cubic number. Cubic in the omega coincides with chi because all of these graphs are perfect. So here's the proof strategy. So we're devising a strategy for algorithm, which sometimes we call online algorithm. And And this strategy will use omega plus 1 choose 2 times 24 omega colors. And a color will be actually a triple, so it will be there will be alpha, beta, and gamma coordinates. All of them will be positive integers, yes, and alpha plus beta will be at most w plus 1, and the gamma will be bounded by 24w. And just from these bounds, you can get that the number of triples like that is as stated. So we just need to put the coloring and prove that it's proper in the online context. So we have these two lines, we fix them to be horizontal, we call them L1 and L2. And then a vertex, presented vertex is a convex set, yes? So this is V, and that's the convex set. It touches V1 at some point, maybe at some interval, I don't care, we choose a point there. That's V1, and we choose V2 on the other line, yes? And now you can draw a segment that connects V1 with V2. That's the segment of our set V. And since the set is convex, the segment is in the set. Now when you have a sequence of vertices, you can think of already presented vertices, then we will say that this is, for example, 1 increasing. If just when you look at the segments, yeah, of the corresponding vertices, it increases on the first line. So there is a left-to-right ordering on the line, the points on the line. So this would be like this, I guess, yeah. Yeah. So these segments, this is 1, 2, 3, coming from V1, from V2, from V3. Yes, that should be. Well, actually, I have drawn more than I claim here, because I have the next thing in mind. So this should be, but then how do they look? It's not specified, yeah? Or this could be like this, yeah? That's V1, that's the endpoint of S1, S2, S3, and so on. Okay, that's 1 increasing, yeah? And then you can have something which is 2 increasing, 1 decreasing, 2 decreasing, and that's all the 4 combinations. So now when presenter introduces a new convex set, right? So V is introduced, yeah? And then we're about to put the color, which is a triple. And the color will consist of alpha V, that will be the first coordinate. This is the maximum size of a sequence of already presented sets, including V. That is 1 increasing, 2 decreasing, and starts with V. So, how does it look like? Well, so say this is a segment of V, yeah? Yeah, this is V, actually V1, right? Now, these other, so if we should think about some candidate sequence. Let's call it V, X, Y, Z. When would be candidate sequence? When it's 1 increasing, so the corresponding segments here, X, Y, Z, start at such points like that. And it's 2 decreasing, so the corresponding thing starts from V and goes here. So this would be X, Y, Z, right? So we can draw an example. Yeah, something like that. That is a sequence of size 4. Yeah, which is 1 increasing, 2 decreasing, and starts with V. So the maximum size of such a sequence that we can see in already presented sets is alpha V. Now beta V is the same, but we look at the 1 decreasing, 2 increasing, starting with V. So to show you the picture here, you know, we start with V. Yeah, and if it would be again some candidate sequence V, X, Y, Z, then it should be 1 decreasing, so this should go like this, X, Y, Z, and 2 increasing, so X, Y, Z, yeah? Okay. So that's beta V. Now, please remember that the actual sets are larger. Yeah, we are dealing with V, which is a convex set. Yeah, that's just a segment here. Yeah, but in order to talk about increasing and decreasing sequences in this context, it's just the segments that matter. And now, given that, algorithm is putting this new vertex or convex set, if you like, into a box, which is alpha v beta v. Yeah, so it's recognized as alpha v beta v, and it's put into the box with that name. Yes, so that is what is happening, and so algorithm puts v in x alpha v beta v, and now within this box applies first bit. Yeah. So you can see that the algorithm actually has lots of first bit strategies running in parallel, and whenever something enters the right box, it feeds the right first bit instance, and that's it. And that's it. So we are going to prove now that the coloring is proper, and that first bit never uses more than 24 W colors. So there are just two claims to do it. First claim is that the segments of sets in the same box are pairwise disjoint. And this has a very easy argument because, well, imagine the opposite, yeah? Imagine that you introduce some segment, some set V, yeah? And its segment actually intersects some segment U of a set already presented, and both of them end up in X alpha beta, yeah? So that will be a problem because U received the second coordinate beta here, so I assume that the red segment is like that. There is another case that is like that, but it's totally symmetric. So U has a segment beta, and perhaps the value of beta was, I don't know, 3, right? So there were two already presented back then sets with segments like this. Yeah, so there would be X and Y. Yeah, so U, X, Y was a sequence that counts for the beta. But now V actually extends this segment, this sequence. So since that was already of length beta, now this is of length beta plus 1, which is a contradiction with the fact that V gets to the alpha beta. So indeed, the segments are pairwise disjoint. And now we have the second property, and the second property is that the poset induced by sets in a fixed box is 3 plus 3 free. So poset induced by the poset induced by X alpha beta is 3 plus 3 free. And this will complete proof because then first fit is efficient, and first fit uses the number of colors, which is 2 times 3 minus 3 times W. So it's 6 minus 3. It's 3. 3W and And times 8. Times 8, that's the number that Pursuit uses in Greek. So it's 24. 24 though. So why is it the case here? Well, note that 2 plus 2 is possible, so they are not interval orders. And let's see how. So I want to show you a 2 and a 2. Yeah. So maybe I have 2 red guys, and I have 2 yellow guys. So comparability here means that the things are disjoint. And actually they all are in the same box, so the segments have to be disjoint. So you can think of 2 red like this. And then the yellow should be inside, I think. And now what you should do is that, so you imagine that these are like this. And, actually not. You should imagine this, you know. Yeah, I screwed it, but I know how to draw it now. So the red set, first red set is like this, second red set is like this, and that's enough. The yellow could be just segments. So that's 2 plus 2. It's possible. But 3 plus 3 is not possible. And why is it so? Well, so imagine that we have a 3 plus 3 structure. Yeah, so we have yellows and we have blues. The segments are pairwise disjoint. Yeah, so there is an ordering of 6 segments here. But when you look at the first 3, there must be 2 yellow or 2 blue. So let's assume that this is 2 yellow. I don't care if there's a blue in the middle or not. And in the last 3, there must be 2 of the opposite color. So say that this is 2 blue. Yeah. And now, so let's call this guy x1. This guy x2, and these guys are y1 and y2. And now I claim that a set of x1 is disjoint with the set of y2. x1 and y2 are disjoint. Which in our language would mean that x1 is less than y2. Yeah, in the Posets, so we would have some comparability here. Yeah. Which would be a contradiction of the existence of a 3 plus 3. So why x1, y2 are disjoint? Well, set x1 is disjoint with set x2. So in particular, x1 is disjoint with the segment of x2. So x1 is shielded by this. Yeah. Now, this segment, by our assumption, is left of this segment. And the segment and the set y2 is disjoint with the set y1. So in particular with the segment of y1. So it's shielded from this side. So we have that this yellow stays disjoint with this blue. Which gives us the contradiction with the assumed existence of 3 plus 3 poset. And this way our strategy for algorithm works and gives cubic number of colors in terms of the optimum. Yeah, that will be it. Thank you.